jewelry diamond detector has these accessories as follows. The first is the mainframe of our computer. The second is the holder for the probe. The third is the tray for measuring the loose stones. The fourth is the reflective white board used for parameter comparison, 2 pieces. The fifth is the probe holder for probe measurement. There are also 2 fiber optic probes. Fiber optic probes are divided into 2 types. One kind of measurement port is 3.0 mm, mainly used for bulk measurement of bare diamonds. The other measuring port is 1.6 mm, which is mainly used for measuring loose diamonds. In the process of measuring broken diamonds, the small fiber optic probe will have less interference with the metal. If the 3.0 mm probe is used to measure loose diamonds, the metal interference will be bigger. Therefore, the 3.0 mm probe is mainly used for bulk measurement of loose diamonds. Let's first test the equipment power on. There is a power switch on the left side of the device. Turn on the power switch. Then we have 2 switches directly in front of the equipment. The blue switch is the UV light source. After opening the blue switch, it takes 8 seconds for the signal to come in. At this point we can see the faint blue light in the integrating sphere. Then we turn on the red button, visible light source button. After opening we can see a bright white light in the integrating sphere. This means that the light source of our device is normally turned on. After the light source is turned on, we use the white part of the white board to align downward with the white light source. Next we will adjust our software. First we have to adjust the integration time, in milliseconds, so that the maximum energy value remains between 40,000 and 50,000. The energy value is too high, we need to reduce the integration time. The energy is too low, we need to increase the integration time, to ensure that the maximum energy value remains between 40,000 and 50,000. Next we have to set the average number of times. The average number of times is calculated by multiplying the adjusted integration time and the average number of times by a total of approximately 500 milliseconds. The integration time in the video example is 60 milliseconds, so the average number of times can be set to 8 multiplied by 480, approximately equal to 500. Smooth width is generally set to 2. Do not need to modify. Other data do not need to modify. After setting these parameters, the software will automatically save. The next time there is no need to set parameters again. Next we click on the yellow light bulb pattern saved as a reference value. After clicking on it, we move the reflective white plate inside the integrating sphere, and then click on the black bulb to save it as a dark current. After these 2 steps, the bottom of the software screen will show that both the reference value and the dark current are green. When both lights are green, we can click our 4 reflection mode. In our reflection mode and with the whiteboard removed, the software's reflection is a parallel line of 0. If the reflective whiteboard is placed again, the software reflection should be a parallel line of 100%. At this point the reflection line is not flat, so you need to click on the yellow bulb again to save it as a reference value. Make the reflection line as a 100% parallel line. This parameter ratio and adjustment can be done at any time during the measurement process. Just make sure that you click on the yellow bulb when the board is placed on it. When the white board is removed, click on the black bulb. Finally, after making these adjustments, we are ready to test the sample. Now we put the samples into the sample chamber in order. The sample is placed in the center of the light source, no other adjustments are needed. After the sample is placed, the software can directly measure the reflection spectrum of the sample. We can determine the authenticity of the sample by identifying the reflection spectrum. This sample is a zircon. Let's try again with a second sample. At this point we can see that after the sample is placed, we can select the sample library and click on the diamond. There will be some reference lines to help identify the sample. This sample has a very obvious downward absorption at 270. We can tell that this sample has been treated with high temperature and pressure, or is a CVD synthetic diamond. For small synthetic diamonds on the market, we can use the GEM-3000 integrating sphere for measurement. But the sphere in the measurement process needs to be put one by one, time-consuming and slow process. This time we can use the fiber optic probe for fast batch measurement. Now we explain how to switch from integrating sphere measurement to fiber optic probe measurement. First of all, the fiber optic probe measurement needs to switch the light source from the integrating sphere to the probe side. Then we must turn off the blue UV light switch button before switching the light source. After closing, toggle the small metal button forward in the dark compartment on the left side of the device. After toggling the device again, open the blue UV light source button. At this point the light source is successfully switched to the fiber optic probe side. Similarly, if we need to switch the light source of the fiber optic probe to the integrating sphere, it is also necessary to first turn off the device's blue UV light source button. At the same time, the small metal button in the dark compartment on the left to dial back. And then open the device's blue UV light source button again. Then the light source is also successfully switched to the integrating sphere. Okay, let's switch the light source to the fiber optic probe again. Step 1, turn off the blue button. Step 2, swing the metal button forward. Step 3, open the blue button. During the whole switching process, the red button does not need to be set. Next, the fiber optic probe connection. In the bifurcated section of the fiber optic probe there is a branch with a thicker end and a single core branch with a thinner end. The multi-core branch is connected by rotating the lighted hole above. Before connecting the single core branch, you need to rotate the original fiber out of the device, and then rotate the branch into the connection. Similarly, to switch back to integrating sphere measurement you need to spin out the single core branch, and then spin in the original blue fiber. After the fiber branch connection we come to the measurement. In the process of measurement we have a reflective probe holder. You need to rotate the reflective white plate in from below. Then turn it upside down on the table. Put the fiber optic probe into the center hole of the reflective probe holder. The corresponding position is the position of the reflective whiteboard. Then open the software for adjustment. Adjust the energy value of the spectrum. The maximum energy value is about 30,000 best. If the energy value is too low, you need to increase the integration time. At the same time, let the average number of times in integration time multiplied by about equal to 500 milliseconds. After setting, click on the yellow bulb pattern to save as a reference value. Then move the fiber optic probe into the small hole on the right side of the probe holder. At this point, a red parallel line will appear on the screen. Click on the black bulb pattern to save as dark current, and then enter the reflection mode for sample measurement. Select the diamond mode in the sample library. At the same time, because the reflectance of the measured sample varies a lot, you need to click the second icon to change the coordinate sequence to automatic measurement mode. Then click on the custom measurement and select diamond mode. The software will automatically determine the results of the measurement. Attach the probe to the probe holder, ensuring that the distance from the probe to the sample stage is about 2 to 3 millimeters. Adjust the position of the probe holder, align the sample and start measuring. The samples are lined up in order, and the first sample plot 270 is seen on the software without a sound. Determine that the sample is a faulty synthetic diamond. Move the sample tray. When the second sample is measured, the software prompts pass with a sound to determine that there is no problem. Move the tray again. The third sample does not sound, and there is no absorption at 270 on the screen. You need to pick out the sample. It may be a 2A type diamond, and you need to make the next determination. Continue to move the tray and pass with a pass and a loud sound. If NG is displayed and there is no sound, pick it out and proceed to the next step. Using fiber optic probes to measure diamonds is very fast. We divide the measured loose stones into 3 categories. The first category is pass with a ringing sound, which is judged to be a pure natural diamond. The second category is NG with no ringing and a downward absorption inflection point at 270 in the spectrum, which is considered problematic. The third category is NG, no ringing, no inflection point at 270 in the spectrum, and an inflection point at 230, which is a natural type 2A diamond. With the equipment we can first classify the samples into these 3 categories. However, natural type 2A diamonds are very rare. In the actual measurement process, we can divide the sample into 2 categories. One category is for natural diamonds with sound. The other category is the problematic diamonds without sound. Then these problematic diamonds will be further tested. How to determine the diamond? Through the observation of the spectrum chart is summarized into 4 kinds. The first type of spectrum, you can see a very obvious 415, while at the 300 position there will be a clear upward rising graph. This spectrum is the standard natural type IA diamond. At 415 there is absorption, at 300 there is an upward extension, 280 to 320 straight between all can be. The second type of spectrum, at 415 there is no absorption, but at 280 to 320 directly there is a clear upward extension chart. This spectrum is also a natural diamond, the software will pass the decision. The third spectrum, the lowest absorption inflection point at 230, no absorption inflection point at 270, and no absorption inflection point at the back. This spectrum can be judged as natural type 2A diamonds, but further testing is needed to confirm in case of emergency. The fourth spectrum, you can also see the inflection point at 230, 230 absorption inflection point can be determined as type 2A diamond. At the same time, there is an inflection point at 270, we need to suspect that this type of diamond has been treated with high temperature and pressure. Currently on the market, diamonds treated with high temperature and pressure and CVD diamonds will have inflection points at 270. We can classify diamonds into these 4 types by spectra. Let's watch it again. The first type of spectrum, with 415, with 300, is the standard natural type IA diamond. The second type of spectrum, none 415, with 300, can also be judged as natural diamonds. The third spectrum, only 230, 270 no absorption, can be judged as natural type 2A diamonds. However, the current counterfeiting technology has improved, for this type of diamonds need to be further tested and then confirmed. The fourth type of spectrum, 230 and 270 absorption, can be determined to be treated or synthetic diamonds. Now for the small probe to measure the broken drill. First of all, you need to rotate the fiber optic wire of the large probe out. The bifurcated fiber optic cable of the small probe is also divided into multi-core fiber and single-core fiber. Connect the multi-core fiber to the connector with the light source on top. Connect the single-core fiber to the connector of the detector below. Put the small probe into the center of the probe holder for reference measurement. Also adjust the energy value to between 20,000 to 30,000. Due to the weak energy of the small probe, it is necessary to increase the integration time. Make sure the energy value can reach above 20,000. Similarly, adjust the average number of times, and the integration time multiplied by about equal to 500. After the adjustment is complete, click on the yellow bulb pattern to save as a reference value. Then the small probe fiber optic moved into the right small hole. Software screen will appear a parallel line, and then click the black bulb to save as a dark current. Click on R to enter reflection mode. At the same time, we can click the second icon to set the coordinate system for automatic tracking. So that we can track and observe the spectral lines during the measurement process. Next, we use the small probe to align with the sample we want to measure. Here we have to be careful not to let the probe touch the diamond. At least a distance of 1 mm must be guaranteed, otherwise the small probe can be easily broken. If we hear the sound and the display pass, then the sample is okay. Then move to test the next sample. If there is no loud sound but the spectrum at 230 and 270 absorption inflection point is a problematic diamond. If there is no sound but the spectrum only has an absorption inflection point at 230, then it is probably a type 2A diamond. We put the fiber optic probe to the sample. The sample is still bright blue-green phosphorescence after the probe is removed. Then the sample must be a problem sample. This sample has 230 but number 270 inflection point on the spectrum and no blue-green phosphorescence. Then the sample is a natural type 2A diamond. To summarize, the selected faulty diamonds are further tested for natural type 2A diamonds and genuine faulty diamonds by phosphorescence testing. If a blue-green phosphorescence is detected, then the diamond must be faulty. A natural type 2A diamond with only 230 inflection points and no blue-green phosphorescence in the spectrum.